Hello everyone and welcome to Lecture 9 of our Probability Theory course. Today we're going to explore one of the most fundamental and important concepts in all of probability theory, the distribution function of a random variable. This concept provides a universal way to describe random variables, regardless of whether they are discrete or continuous. Here's our plan for today. We'll begin with a brief review of discrete random variables and understand why we need a more universal description. Then we'll define the distribution function f of x and examine its four essential properties. We'll see how f of x works for discrete random variables and look at its graphical representation as a step function. We'll work through two detailed examples, constructing f of x and using it to find probabilities. Finally, we'll get a preview of how the distribution function works for continuous variables and explore its relationship with the probability density function. Before we introduce the distribution function, let's quickly review what we've learned about discrete random variables. We studied them using the distribution series, a table that lists all possible values and their corresponding probabilities. We also used the distribution polygon as a graphical representation. We calculated the expectation, which is the weighted average of all values, and the variance, which measures the spread. But here's the critical limitation. All these methods work well for discrete variables, but they cannot be used for continuous variables. For continuous variables, we cannot list all possible values because there are infinitely many in any interval, so we need a completely different approach, one that works universally for all types of random variables. So why do we need a universal description? The problem is that different types of random variables require different descriptions. For discrete variables, we can use a table of values and probabilities. For continuous variables, we cannot list all values because there are uncountably infinitely many. We need a unified approach that works for both. The solution is the distribution function. This function has several advantages. It works for both discrete and continuous random variables. It gives a complete probabilistic description. It allows us to calculate probabilities easily, and it has elegant mathematical properties. The distribution function is widely considered the most important concept in probability theory because it provides this universal framework. Let's now define the distribution function formally. The distribution function, also called the cumulative distribution function or CDF of a random variable x, is denoted by f of x and is defined as the probability that x takes a value less than or equal to x. In symbols, f of x equals p of x less than or equal to x. This definition holds for all real numbers x. The interpretation is simple. F of x accumulates all the probability up to the point x. For example, f of 0 is the probability that x is at most 0. F of 5 is the probability that x is at most 5. The key idea is that f of x gives us the cumulative probability from negative infinity up to x. The distribution function has four essential properties that characterize any valid CDF. First, boundedness. F of x is always between 0 and 1 inclusive for all real x. Second, monotonicity. F is non-decreasing, meaning that if x1 is less than x2, then f of x1 is less than or equal to f of x2. As x increases, the probability accumulates and never decreases. Third, limits. As x approaches negative infinity, f of x approaches 0, and as x approaches positive infinity, f of x approaches 1. This makes sense because at negative infinity, we've accumulated no probability, and at positive infinity, we've accumulated all probability. Fourth, right continuity. F is right continuous at every point. These four properties completely characterize any valid distribution function. Now let's see how the distribution function works for discrete random variables. For a discrete variable with a distribution series, f of x is the sum of all probabilities for values less than or equal to x. In other words, we add up all p sub I for which x sub I is less than or equal to x. Let's look at the coin toss example where we toss a coin twice and x is the number of heads. The probabilities are 1/4 for 0 heads, 1/2 for 1 head, and 1/4 for 2 heads. To construct f of x, we start with f of x equals 0 for x less than 0. Then for x between 0 and 1, f of x equals 1/4. For x between 1 and 2, f of x equals 3/4. And for x greater than or equal to 2, f of x equals 1. Notice that f of x jumps at each possible value. This is why f of x is called a step function for discrete variables. The step function representation is very characteristic of discrete random variables. The function stays constant between possible values and jumps at each value. The size of the jump at x sub I equals the probability that x equals x sub I. The function is right continuous, meaning that at each jump, the function takes the higher value. This graphical representation is very useful. It clearly shows where the probabilities are concentrated and how they accumulate. The larger the jump, the more probability is concentrated at that point. This visual representation helps us understand the structure of the distribution at a glance. Let's work through a detailed example. We'll use our familiar defective items problem. A factory produces items with defect probability 0.1. We select 3 items and x is the number of defective items. The distribution is probability of 0 defectives is 0.729, of 1 is 0.243, of 2 is 0.027, and of 3 is 0.001. To construct f of x, we calculate cumulative probabilities. For x less than 0, f of x equals 0. For x between 0 and 1, f of x equals 0.729. For x between 1 and 2, f of x equals 0.729 plus 0.243, which is 0.972. For x between 2 and 3, f of x equals 0.972 plus 0.027, which is 0.999. And for x greater than or equal to 3, f of x equals 0.999 plus 0.001, which is exactly 1. Notice the jumps at 0, 1, 2, and 3 with jump sizes 0.729, 0.243, 0.027, and 0.001 respectively. Now let's use f of x to find various probabilities. First, the probability that x is less than or equal to 1 is simply f of 1, which equals 0.972. Second, the probability that x is greater than 1 is 1 minus f of 1, because x greater than 1 is the complement of x less than or equal to 1. So that's 1 minus 0.972, which equals 0.028. Third, the probability that x is between 1 and 2 inclusive is f of 2 minus f of 0. That's 0.999 minus 0.729, which equals 0.270. We can verify this directly. P of x equals 1 plus P of x equals 2, which is 0.243 plus 0.027, also 0.270. So the formulas work perfectly. The general formulas we'll use are P of x less than or equal to x equals f of x. P of x greater than x equals 1 minus f of x. And P of a less than x less than or equal to b equals f of b minus f of a. Let me give you a preview of how the distribution function works for continuous variables. For continuous random variables, f of x is a continuous function. There are no jumps. The graph is a smooth curve that increases from 0 to 1. The key differences from discrete variables are there are no jumps, the function is differentiable, the probability that x equals any specific value a is exactly 0, and we use a probability density function instead of individual probabilities. The density function, denoted by f of x, is the derivative of f of x. This relationship between f and f is fundamental in continuous probability theory. We'll explore continuous variables in much more detail in our next lectures. The relationship between the distribution function and the density function for continuous variables is very elegant. First, the density function f of x is the derivative of the distribution function f of x. Second, the distribution function f of x is the integral of the density function from negative infinity to x. Third, the probability that x lies between a and b is f of b minus f of a, which equals the integral of the density function from a to b. The density function f of x has 2 key properties. It's non-negative everywhere, and its integral over the entire real line equals 1. This mirrors the properties of the distribution series for discrete variables, but using calculus instead of summation. We'll study these concepts in detail when we cover continuous random variables. Let me summarize everything we've learned today. The distribution function f of x is defined as the probability that x is less than or equal to x. It has 4 key properties. It's bounded between 0 and 1, it's non-decreasing, its limits at negative and positive infinity are 0 and 1 respectively, and it's right continuous. For discrete variables, f of x is a step function with jumps at each possible value, and the jump size equals the probability of that value. For continuous variables, f of x is a continuous function, and its derivative is the density function. We also learned how to use f of x to find probabilities. The key takeaway is that the distribution function provides a universal description that works for all types of random variables. Now let's look at how the distribution function works for continuous random variables. This is a preview of what we'll study in much more detail in our upcoming lectures. For continuous random variables, the distribution function f of x is a continuous function. Unlike discrete variables where we had jumps at each possible value, for continuous variables there are no jumps at all. The function is smooth and increases continuously from 0 to 1. Let me highlight the key differences between discrete and continuous variables. First, for continuous variables, f of x has no jumps. It's a continuous function everywhere. Second, f of x is differentiable except possibly at some points. This differentiability is what allows us to define the probability density function. Third, and this is a very important point, the probability that x equals any specific value a is exactly 0. This might seem counterintuitive at first. For a continuous random variable, the probability of any exact value is 0 because there are infinitely many possible values. Instead of probabilities of exact values, we talk about probabilities of intervals. Fourth, instead of using individual probabilities like we did for discrete variables, we use a probability density function denoted by f of x. The density function is not a probability itself. It's a function that describes how probability is distributed across the range of possible values. The connection between the distribution function and the density function is elegant and simple. The density function f of x is the derivative of the distribution function f of x. This relationship is fundamental in continuous probability theory. If you know f of x, you can find f of x by differentiation. Conversely, if you know f of x, you can find f of x by integration. Now let's explore the relationship between the distribution function and the density function in more detail. There are three key relationships that you need to understand. First, the density function can be obtained from the distribution function by differentiation. That is, f of x equals the derivative of f of x with respect to x. This means that the density is the rate at which the cumulative probability is increasing at any point. Where the distribution function is steep, the density is high. Where it's flat, the density is low or 0. Second, the distribution function can be obtained from the density function by integration. F of x equals the integral of f of t dt from negative infinity to x. This represents the accumulated probability up to point x. It's the continuous analog of summing probabilities in the discrete case. The integral accumulates the density from the far left up to the point x, giving us the total probability that x is less than or equal to x. Third, the probability that x lies in an interval from a to b is f of b minus f of a, which equals the integral of f of x dx from a to b. This is a very important formula. Geometrically, this represents the area under the density curve between a and b. The total area under the entire density curve is 1, and the area between a and b gives us the probability that x falls in that interval. Now let's discuss the key properties of the density function f of x. First, the density function is always non-negative. This makes sense because probability cannot be negative. The density function can be greater than 1. Unlike probabilities, it's not a probability itself. It's a density. Second, the integral of the density function over the entire real line equals 1. This is the continuous version of the normalization condition we had for discrete variables. The total probability over all possible values must sum to 1, and in the continuous case, this sum becomes an integral. These relationships between f of x and f of x are absolutely fundamental in probability theory and statistics. They allow us to move back and forth between the distribution function, which gives us cumulative probabilities, and the density function, which describes the local concentration of probability. That concludes our lecture on the distribution function. Thank you very much for your attention. This concept is absolutely fundamental to all of probability and statistics, so please make sure you understand it well. In our next lecture, we'll study continuous random variables and probability density functions in detail. See you then.